Okay, sometimes when we look at a problem for conservation of energy, the system is an open system, which means that energy can either enter the system or leave the system. And so I want to show you guys how you might set up something like that. I've already drawn out an LOL chart for us, and we have a package of tamales sliding into a spring. It's getting stopped, and as the spring compresses it, some energy goes into friction, and so essentially it's creating thermal energy. It's heating up the environment. Think about if you rub your hands here, they heat up. That's the work you do when you rub your hands is converted into thermal energy there. Okay, so we compress the spring and we're brought to a stop. Alright, so if we are sliding along though, that would mean that we have kinetic energy. So I'm going to draw some kinetic energy right here. Okay, and as it comes to a stop, that kinetic energy is going to be transformed into elastic potential energy. However, not all that kinetic energy will go to elastic potential energy because some of it's going to leave the system as thermal energy. Okay, and so that's how we'd show that. And what that means is that afterward, so say we had 3 boxes of energy to start, now our system actually has less energy in it. We only have 2 boxes now, okay, because some of that energy was taken by friction. Alright, so the next step would be to use this diagram to construct an equation. So for kinetic energy, we write 1/2 mv squared. For elastic potential energy, that's 1/2 kx squared. And we'll show work done by friction, and we're going to put it on the right side because it's leaving the system. If there's work being done to put energy into the system, we put it on the left. When it leaves the system, we'll put it on the right. Okay, so here we have our equation written out. Kinetic energy on the left, elastic potential energy on the right, and it would be just that, except that we're adding this to the right as well because some of that energy left the system in the form of thermal energy. Okay, which is just useless energy, we can't get it back. So the goal here is to find out how much energy was lost to heat or friction. That's our thermal energy. So we're going to solve for that. So we'll subtract over the 1/2 kx squared, and we can substitute in these values we got for the spring compression, 5.5 centimeters, which would be 0.055 meters. We have our spring constant. We have the mass of the package, and we have the initial speed. Now, at the end, we know that kinetic energy is 0 because it says that it's going to be stopped after compressing the spring. Okay, so let's go ahead and substitute those in and solve. So I've gone ahead and moved over the elastic potential energy to the other side. Let's substitute our values and see how much of each we have and use that to solve for our thermal energy. Okay, so to continue, we've now found that the kinetic energy is 16 joules and the elastic potential energy was 15.125 joules. So we can subtract those and we find that the thermal energy is equal to about 0.875, or we'll say 0.88 joules. Okay, and we'll say that this is about maybe 5% of the energy that has actually gone to thermal energy. Okay, and so some of that energy was lost as the spring was compressed, and that's energy that won't come back again. Alright, it's turned into heat essentially. So the second part of this question is, well, what is the coefficient of friction? So we can use this. If we have work done by friction, that will be the energy gone to thermal energy, and we know the relationship for work between the force and the distance is F times X. Okay, and this is negative work because it's energy coming out of the system. We don't have to get too crazy with the negative signs here just because we know that this is energy that's already lost. So for frictional force, the coefficient, in this case it'll be just mg since it's on a flat surface and nothing's pulling up on it or down on it, and then our distance will be the same x, so 0.055. So we can actually solve for mu here, our coefficient of friction, knowing that the work done by friction was 0.88 joules, and given these values that we already know. Okay, so we divide all these over, and we'll find that mu is equal to So we find the coefficient of friction is equal to about 0.82, and those are newtons per newtons if you care about the unit there. We can divide that one out. So we found, though, the coefficient of friction here given the amount of energy lost. Okay, and so then we said, okay, the energy lost would be equal to the work done by friction. We can see the work done by friction, since it's a uniform force, would be the force times the distance. We can substitute in our values and solve for mu. Okay, we're going to look at a slightly more complicated situation now. We have an object that's at rest. It gets pushed with a 15 Newton force, causing it to slide. It will slide up a ramp to a platform that's 0.5 meters higher than it started, where it's going to slide to a stop 2 meters later from friction between the object and the ground. If there's a coefficient of friction of 0.4, the question is, how far was that object pushed initially? Okay, well, the simplest way to do this is going to start by thinking about our system and the energy we start with and that we finish with. Okay, so if we look at our system, it's going to be made up of the Earth, because we're going to end up with some gravitational potential energy, and the object, okay, the object that's going to get that gravitational potential energy. Alright, we do have to, so when we look at the beginning though, the object's just sitting there. It's at rest. It doesn't have any energy at all. It's just sitting there. Okay, we're going to say that initial height is height 0, so 0 potential energy. Well, it gets pushed, which means that potential energy is going to increase. Okay, it's going to go up. Well, that energy has to come from somewhere, and in this case it's going to come from work done by an applied force. So this is work from the force. Okay, that applied force. That energy from that applied force is going to go into the object, and at the end it's going to have potential energy because of it. These 2 bars that I gave it here for potential energy. However, there was a little bit more energy, and if there was no thermal energy, then the rest of it would have probably gone to kinetic, and it would still be sliding. Kinetic energy. But it's not sliding. It came to a stop, which means the energy was lost. And so in that case, that energy would have left the system as thermal energy, which means that we don't have as much energy as we were initially given. So we've got this all diagrammed here. Now we're going to write our equation. At the beginning we have work from the force that was applied. At the end we have gravitational potential energy, and then we have energy that went into friction, heating up the ground or the object. Thermal energy. So the energy that was added to the system I put on the left. The energy that was lost I put on the right. We had nothing before, so we have nothing here in addition to the work, and we're left with gravitational potential energy. So now we can go ahead and write out our equations. For work, it would be the force times the distance. It's a uniform force. For potential energy, mgh. And for thermal energy, it'll be friction times the distance. So in this question, we actually have 3 different distances, so we got to be careful not to confuse them. I'm calling the distance at the beginning d, the height that it goes h, and that distance that it slides at the end x. Okay, I know this, I know that, I know this, I know this, and that, and I know this force, and I want to solve for d. Okay, the friction, remember we're going to use the fun equation. So F is equal to mu times the normal force, which since it's on a flat surface is just going to be m times g. So we'll plug all this in, we'll divide by F, and solve for d. Before we can actually solve this, I just realized I didn't provide the mass for this question. So let's say the object has a mass of 2 kilograms, and this will allow us to solve for all the missing information. So let's go ahead. I'm actually going to substitute in the values and get the quantities first. I'm going to substitute in all of these and find the work by friction. I'm going to find potential energy, and then I'm going to solve for d. So I found that we ended up with about 9.8 joules of gravitational potential energy. We lost 15.7 joules to thermal energy, and we're going to go ahead and solve for d. So we'll add these together and get about 25.5 joules. We'll divide by the distance, or the force, I'm sorry, to find d now. So we'll divide that 25.5 by 15. And we find that the distance that it was pushed was about 1.7 meters. So what that means is when that object first started moving, something was pushing it and continued pushing it for over a distance of 1.7 meters before releasing it. Then it eventually slid up onto a ramp and it was caused to stop by the work from friction. Okay, so we get this distance of 1.7 meters.